All right, now that you've been through and you know discrete time convolution, your life is never going to be the same. Turns out there's an analogous procedure for continuous time convolution. So let's check it out. Now, this is the equation y of t, we say, is the convolution of x with h, and we use the asterisk again. And this is the operation itself. This is the convolution integral. More on that in a second. But before we get to the mathematical details, let's understand the engineering. We're saying that if we have a linear time-invariant system and we put in a signal x, we want to know what do we get out of the system. Okay? So I'm not going to do a circuit analysis. I'm not going to do vibrational analysis or mechanical analysis. I'm not going to analyze an acoustic system. Okay? It turns out all I need to know, other than the system is linear time invariant, is how it responds to this little tiny disturbance, the impulse. How does it respond to the impulse? We call that the impulse response h of t. So that's given. So if you're given the impulse response h, and you're given that it's linear time invariant system, then if I want the output y, I need to perform this convolution x with h, and here it is. This is the convolution. I'm going to write the convolution sum from discrete time. Okay? It looks like this. Let's draw some comparisons now between the two. Let's try to understand it. First of all, we said that this in discrete time is a function of n. This, the n, is playing the role of t here, if you just make the comparison. So this thing turns out is a function of t, y of t equals this. So here, notice we sum over minus infinity to infinity. The sum becomes, in continuous time, an integral. An integral is nothing but an infinitesimally spaced sum. So the sum becomes an integral from minus infinity to infinity. Here in discrete time, we summed over k, and the k's go away. You plug in values of k and then they go away. Here we're going to integrate over this dummy variable tau. So k plays the role of tau. And I call it a dummy variable because, again, when you integrate and then plug in bounds, the tau's go away. So it really doesn't matter what you call it, as long as you don't call it t. So we're going to call it tau. So tau goes from minus infinity to infinity, just like k went from minus infinity to infinity. Okay, and then we have x of tau, x of k, h of t minus tau, h of n minus k. So I'll just make one more comment. Our strategy of flipping h, right, and plotting it versus k. So we flipped h of k, and then flipping and shifting, right? Well, and remember where we got flipping and shifting. We said, okay, well, this dummy variable k looks like the dependent variable x of k and h of k. So we see that the k appears with minus, so that's why we flipped it, and then we shift it by n. So same thing here. Tau is now we can take the perspective of being the independent variable. So x of tau, h of minus tau. So we're going to flip it. We're going to plot it versus tau, flip it, minus tau, shift it by t. So the strategy of flipping h and shifting it still holds. Okay, and that's the method. That's the main method that we're going to use to solve these convolution problems, which are can be found in the next few examples. So let's check them out.